America's mighty flying fortress is one of the most potent aerial offensive weapons yet devised. Its effective bomb load runs into tons of high explosives. Its crew has received months of intensive and costly training. It is capable of long flights across oceans and continents. This enormous investment in equipment and training has but one purpose: to get the bombardier where he can drop his deadly load with the most devastating effect. If this investment in men and dollars is to achieve its objective, the bombardier must produce results. The success of the mission depends on how well he applies what he has learned of the theory of bombing. The theory of bombing, all important in the science of war, must be carefully studied and clearly understood to achieve decisive results. A common physics experiment will help to grasp properly the basic theory of bombing. On a perfectly leveled surface, it is possible to visualize a fundamental law of physics. Any body will continue its uniform motion in a straight line unless affected by an external force. Thus, on the leveled plate, a ball will keep rolling until affected by friction. So, if there were no external force, such as gravity, a perfect bomb, one having no air resistance, would continue on with the airplane. But gravity pulls the bomb downward, and the velocity of the airplane propels it forward. The resultant of these two forces forms a line of sight to the target. A second well-known physics experiment, in which air is pumped from a glass tube, illustrates another basic theory of bombing: rate of fall. When all the air has been pumped out, a coin and a feather will drop at the same rate. The slow-motion camera illustrates this principle. Thus, from a stationary object like a balloon, the time of fall of a theoretically perfect bomb, dropped as if in a vacuum, can be accurately figured by considering only the distance it has to fall. Encountering no air resistance, it would fall 16 feet the first second, 48 feet the next second, and 80 feet the third second, accelerating at a uniform rate. A final experiment in the physics laboratory emphasizes still another important fact: identical falling objects will strike the Earth at the same time, regardless of trajectory. Thus, if the perfect bomb is dropped from a moving airplane, it will continue to move forward at the same rate of speed as the airplane, with the exception that gravity, the only outside force in this theoretical situation, will pull it downward at the same speed as the bomb dropped from the balloon. The calculations involved here are quite simple. Since the bomb moves forward as fast as the airplane, and since it has a specific time of fall, depending on the altitude from which it is dropped, the time of fall multiplied by the speed of the airplane gives the whole range, the distance the bomb travels forward during its fall. If these were all the factors a bombardier had to consider, his problem would be easy to solve. However, there is no perfect bomb. Even the best bombs are slowed up by vertical and horizontal air resistance. Thus, when an actual bomb falls from a moving airplane, its horizontal speed will gradually lessen. Because of air resistance, it will trail the airplane and hit the ground some distance behind the airplane. This distance is known as trail. The horizontal distance the bomb has traveled is known as the actual range. Since trail plus the actual range equals the whole range, it can be computed by modifying the simple whole range formula to read time of fall times speed of airplanes minus trail equals actual range. The bombing table supplied by the Ordnance Department give the trail, range, and time of fall for every type of bomb. The bombardier should familiarize himself with these tables. The speed with which he approaches the target is also vitally important to the bombardier. This is called the velocity of closing. Three factors influence the velocity of closing: the speed of the airplane, the speed and direction of the target, and the direction and force of the wind. If the target is stationary and the bomber is flying at 200 miles per hour in still air, the velocity of closing will be 200 miles per hour. However, a 30 mile per hour tailwind will increase the speed of the airplane toward the target to 230 miles per hour. Thus, the velocity of closing will be 230 miles per hour. A 30-mile-an-hour headwind will have just the opposite effect. It will decrease the speed of the airplane toward the target by 30 miles. Thus, the velocity of closing will be 170 miles per hour. Moving targets have exactly the same effect as wind upon the velocity of closing. If the target at 30 miles an hour is approaching the airplane flying at 200 miles per hour in still air, the velocity of closing will be the sum of both speeds, 230 miles per hour. If the target is retreating at 30 miles per hour, the velocity of closing will be reduced to 170 miles per hour. Thus, the velocity of closing is equal to the speed of the airplane minus headwind, or speed of retreating target, or plus tailwind, or speed of approaching target. In general, the velocity of closing is reduced by headwinds or retreating targets, and increased by tailwinds and approaching targets. Crosswinds create another problem. Pilots and students of air navigation are familiar with the fact that the nose of an airplane is not always pointed in the direction the airplane is going in relation to the ground. In order to fully understand this, let us imagine a block of air immediately over the landscape. If a free balloon is placed in a block of air, and if the air moves, thereby becoming wind, the balloon will move with it and travel over the ground. However, in relation to the air, the balloon is not moving. It remains stationary. If the wind or block of air is at rest, and instead of a balloon we assume an airplane, the airplane can fly through the block of air from point to point. But if the air moves, it carries the airplane with it, and the airplane travels in a direction entirely different from the direction in which it is heading. Therefore, to fly in a straight line between these 2 points on the ground, it must head into the wind. Now then, if the airplane flies through the block of still air and drops a bomb during its flight, the bomb will trail directly behind the airplane. Even though the air moves, becoming wind, the bomb still trails directly behind the airplane. But although the bomb is always directly behind the airplane, it does not fall along the track, but instead along the heading line. Crabbing along its track, as a result of the wind, the same situation prevails. From this, it becomes obvious that because the bomb falls directly behind the airplane, it must necessarily fall downwind of the track. Therefore, if the track passes over the target, the bomb will miss, falling downwind. To score a hit, the airplane must fly this distance upwind of the target. To sum up, the effect of a crosswind upon a bomb's trajectory can be easily understood if several basic factors are visualized. In allowing for a crosswind, the pilot crabs along a given track. The bomb's flight is always along the line formed by the heading, regardless of the track. Thus, the bomb will fall downwind along the axis of the airplane. The distance the bomb falls to the rear along the airplane's heading we already know as the trail. The vertical view of the distance between the trail and track is called the cross trail. On an actual bombing run, cross trail is a vital factor. To compensate for it, the bombardier must fly upwind by a distance equal to the cross trail. Once he visualizes the effect of a crosswind, the bombardier is helped materially in understanding the bombing problem. As the present war has illustrated time and again, bombardiers who fail to understand cross-trail correction may drop their bombs wide of the target. Moving targets create another problem. In order to drop a bomb upon a moving target, it is necessary for the bomber to intercept it. It might appear this could be solved by a simple stern chase, flying in a large arc and eventually overtaking the target from the rear. This method, however, takes too much time, for with constant anti-aircraft fire menacing the bomber, every second counts. Therefore, the trained bombardier always takes the shortest possible course to intercept the target. This operation is called establishing the collision course. For example, a fleet of bombers over the ocean observes a warship steaming directly across its course and desires to intercept it. We know that a simple stern chase is not the thing, so the bombardier estimates the speed of the target and plots its probable position at the end of, say, 10 minutes. A line is drawn from this position parallel to the original line between bomber and target. Since the bombardier knows the actual speed of his airplane, he swings an arc through the probable position line equal to the bomber's range in the given 10 minutes. The point of interception gives the bearing through which the collision course is plotted. The line extended from the bomber to the probable course of the warship fixes the point of interception. Once on a collision course, the airplane maintains what is called a line of constant bearing with the target. The angles between this line, the course of the target, and the course of the airplane never change. The bombardier's problem can be summed up in this manner. Here is a target to be bombed. On any given approach, at any given speed and altitude, there is only one point at which a bomb can be released to secure a hit. To determine that point is to solve the bombing problem. Instruments assist the bombardier in the solution. The altimeter, for example, furnishing aid in determining the altitude. Bombing tables, once the altitude is known, give the time of fall and trail for each type of bomb. By correlating airplane speed and the direction and force of the wind, the closing velocity and cross trail are found. The bombardier can then plot his approach to the target, allow for trail, and correct for cross trail. Knowing his bomb's time of fall from that altitude, say 20 seconds, and the speed with which he is closing upon target, by measuring off the equivalent of 20 seconds time of closing, he can determine the point of release. Of course, crosswinds and moving targets introduce many complications, too difficult to compute under actual bombing conditions. Therefore, several bomb sites are employed by the United States Air Forces, which will solve these problems with amazing rapidity and accuracy. But even with these superior aids, the bombardier needs a thorough understanding of the basic theory of bombing to operate the bomb site with its most deadly efficiency.